This is Dr.BDY Sunil, Associate Professor, Mechanical Engineering Department, Institute of Aeronautical Engineering, Hyderabad. In today's session, we will be learning about the mass moment of inertia, parallel axis theorem, transfer formula, mass moment of inertia of composite bodies. The course outcome of today's session would be calculate moment of inertia and mass moment of inertia of a circular plate, cylinder, cone, and sphere from the first principles. The topic covered would be mass moment of inertia, parallel axis theorem or transfer formula, mass moment of inertia of composite bodies. The topic learning outcome is understand the concept of moment of inertia and mass moment of inertia involved in practical engineering problems. First, let us understand both the product of inertia and transfer formula. The product of inertia, which is going to be considered, you consider the object which is placed here and the elemental area here as dA, which is lying at a distance of y and x from the y-axis and x-axis as shown here. Now, the product of inertia for area dA, okay, the product of inertia for area dA is defined as dIxy. dIxy as x into y into dA. As you can remember, the moment of inertia of anything, let us say with respect to x axis, generally it is written as area into distance square. Okay, area into distance square. Here also that it is nothing but it is the area into distance square, nothing but distance into distance. So the product of inertia can be written for this particular area, first for this particular elemental area with respect to both axes combined. Here we are considering the moment of inertia with respect to both axes combined at a time. So we can write that moment of inertia as dIxy. That means with respect to x-axis as well as the y-axis, it can be written as the area. Area is nothing but dA, which we are considering, and the distances are x and y. So this is what that is being given here. For the both axes which is being considered at a time, we will be writing the product of inertia, not the moment of inertia alone. We will be considering the product of inertia for both axes considered at a time. The product of inertia for entire area would be Ixy, that is equal to integral xy into dA. So the transfer formula for product of inertia that is being considered like this. Using the parallel axis theorem for product of inertia is similar to the parallel axis theorem for moment of inertia and is expressed as Ixy is equal to Igx dash y dash plus Ahx hy. So the similarity, you can observe the similarity here. Only thing we are considering the both axes at a time. This relation is called as the transfer formula for product of inertia. The term Igx dash y dash is the product of inertia with respect to the centroidal axis. Now coming to the mass moment of inertia, let us consider the total mass, the solid object, three-dimensional object which we are considering. Till now, whatever we have seen, that is moment of inertia is for the two-dimensional sections, two-dimensional planes, which is also called as the moment of area, second moment of area. So moment of inertia are called as the second moment of area. Here the mass moment of inertia, this is related to the total mass, three-dimensional objects that is being considered. So consider a body of mass m and dm is the mass of an element of this body situated at a distance r from the axis AA as shown in figure. So observe the figure here. The elemental mass dm is being considered at a distance of r from the axis AA. The moment of inertia of body with respect to AA is defined by the equation I is equal to integral r square dm. Again here mass into distance square. In the previous case, that is area into distance square. Here it is taken as mass into distance square and the units are kg meter square. Also the radius of gyration k of a body with respect to AA is given as k is equal to under root I by m. That is related to the radius of gyration k. Now mass moment of inertia for parallel axis theorem. Mass moment of inertia's parallel axis theorem is similar here. According to the theorem, IAB. Observe the figure here. The reference axis is considered as AB and XX is the centroidal axis and the distance between centroidal axis and the reference axis is h. So according to this theorem, parallel axis theorem, we can write IAB is equal to Ig plus mh square, where the area is replaced with mass here. Now let us identify the mass moment of inertia of a circular plane. circular plate, we are going to derive this mass moment of inertia of the circular plate using the basic principles. So the mass moment of inertia of circular plate about its axis of rotation is considered here. Consider a circular plate of radius r and thickness t having mass m. The x and y axis are along the plane of the plate at the centroid of the plate. Okay. Z axis is the perpendicular to the plane of the plate passing through the centroid of the plate. Consider a small elemental circular ring on the plate having a thickness of dr at a distance of r from the center with a mass dm for the ring. The mass is given as dm is equal to density into volume. Okay, so the small mass which is being considered dm, that its representation can be taken as density into volume, where volume again it is being transferred to thickness of the plate as well as the dA, area of the plate. So that can be written as rho into t, that is thickness, into 2 pi r, that is the area of that circular plate, into dr is the thickness which we are considering. Now the polar moment of inertia of the elemental ring, that elemental ring which we have considered, you can observe the second figure. The polar moment of inertia of the elemental ring is dizz is equal to mass into distance square. That can be written as rho t 2 pi r dr into r square. Okay, distance is r and the mass can be treated as density into volume. So that can be written as rho t 2 pi r cube dr. The polar moment of inertia of total circular plate is izz is equal to rho t 2 pi integral 0 to r cube dr. That is equal to rho t 2 pi r power 4 by 4. That is equal to rho t pi r square by r square by r. So we are dividing that r square into r square. So this r square, pi r square can be treated as the area. So we can write rho t a into r square by 2. So again it can be treated as volume, rho into volume into r square by r. So rho into volume again is the mass. So the polar moment of inertia izz of this circular plate can be obtained as mr square by 2. Now the mass moment of inertia of the circular plate with respect to the axis along the section x and y. We know that izz is equal to ixx plus iyy. Hence, as per the plate is symmetrical about x and y axis, ixx would be equal to iyy. So it can be treated as 2ixx or 2iyy, which gives finally the value of ixx and iyy considered again will be izz by 2. So the value of izz is already we have obtained as mr square by 2. So still dividing it by 2, we will be obtaining the mass moment of inertia with respect to x-axis or y-axis as mr square by 4. So this is the value of mass moment of inertia of circular plate. Now let us derive the mass moment of inertia of the solid cone. Mass moment of inertia of solid cone, as we have done it for the center of gravity of the solid cone, again we are taking the same orientation. The axis of rotation is x and the reference axis y and z are shown in the figure. The height of the right circular cone is h and the radius is capital R. Now, the mass moment of inertia of solid cone of height h and base radius r about its axis of rotation we are calculating. From the geometry, we can observe that r by x is equal to r by h, again from similar triangles. So, r is equal to capital R into x by h. From this, the moment of inertia of a circular lamina about x-axis is equal to mr square by 2. Just now we have derived that. That is equal to density into volume into r square by 2. If you further simplify this, the density is rho into a volume, we are treating it as area into thickness into r square by 2. Hence, it evaluates as 1 by 2 rho pi r power 4 into x power 4 by h power 4 into dx. So, moment of inertia of cone about x-axis, that is axis of rotation, can be treated as ixx is equal to 1 by 2 rho pi r power 4 by h power 4 integral 0 to h x power 4 into dx. So, if you further simplify this, you simplify the integration part, you will be obtaining the value as 1 by 2 rho pi r power 4 h by 5. So, further simplification 3 into 1 by 3. If you multiply and divide the term with the 3, 1 by 3 rho pi r square h into 3 into r square by 10, you will be obtaining this 1 by 3 rho pi r square h as the mass of the cone m. So the moment of inertia of this right circular cone with respect to the x axis is obtained as 3 by 10 mr square. This is the value of moment of inertia with respect to the axis of rotation. So similarly, by using the same principle of basic principles, we can derive the values for various types of regular solids here. The circular disc, you can obtain the value of Ix, Iy and Iz as mr square by 4, mr square by 4, mr square by 2 respectively. For sphere having the radius r, you can get the mass moment of inertia as 2 by 5 mr square, 2 by 5 mr square and 2 by 5 mr square. Right circular cylinder, again m by 12, 3r square plus l square, m by 12, 3r square plus l square, m by 2 r square for x-axis, y-axis and z-axis respectively. And for right circular cone, 3m by 10 r square, 3m by 5 r square by 4 plus h square, 3m by 5 r square by 4 plus h square for x, y, z, z-axis respectively. Then slender bar, 0 for as it is a symmetrical axis, and then m l square by 12 and m l square by 12. Then mass moment of inertia of regular rectangular plate. Rectangular plate mb square by 12, ma square by 12, ma square plus b square by 12. Here also you need to always compulsorily consider the reference axis. So rectangular prism, when you consider the reference axis Ix, Iy and Iz, it is mb square plus c square by 12, ma square plus c square by 12, ma square plus b square by 12. So this concludes the session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.